So, why do we need to think about when we come to consider chemical calculations? Well, atoms are really small. So, what we do is we take a carbon atom, and in particular, we take the carbon 12 isotope. So, that one's got 6 protons and 6 neutrons in its nucleus, and we give that a mass of 12. And we compare all other atoms against that. So, if that atom has a mass of 12, a hydrogen atom has a mass of 1, and a chlorine atom has a mass of 35.5. Now that may seem a little bit odd. How can you get an atom with a mass of 35.5? Well, it's because that's the average mass of a chlorine atom. And we need to remember that we have isotopes of chlorine. We have chlorine 35 and chlorine 37. And when we come to look at the weighted mean mass, we find out that it's actually 35.5. You need to know the definition for relative atomic mass, relative molecular mass, and relative formula mass. The key difference is relative atomic mass is atoms, funnily enough. Molecular mass is molecules, and relative formula mass are for ionic species. So let's say I've got a diamond of carbon 12 atoms, and that diamond weighs 12 grams. Now, not only would I be a very wealthy person, but I would also have exactly 6.023 times 10 to the 23 atoms of carbon 12 in that diamond. Because the mass of all other atoms is relative to carbon 12, if I now take the relative atomic mass of sulfur, which is 32.1, and weigh out 32.1 grams of sulfur, I would have exactly 6.023 times 10 to the 23 atoms of sulfur. Now that's a big number, and it's a big number because atoms are so small, and we call that number, bizarrely enough, a mole. So you can think of it a bit like a dozen. A dozen we know is 12. Well, a mole is 6.023 times 10 to the 23. The number of moles of a substance is its mass in grams divided by its molar mass. So let's say my mole weighs 20 grams. That's its molar mass, the number of grams per mole. If I now weigh out 70 grams, I will have 3.3 moles. Now that sounds a bit mean, but remember, of course, a mole is a number. Therefore, 3.5 moles of anything is 3.5 times 6 times 10 to the 23. A very large number of 2.11 times 10 to the 24. And that's the same as 3.5 moles. Now that's very handy for solids, which we can weigh out. However, for gases, not quite so useful. For gases, we use the ideal gas equation to help us. Now, the ideal gas equation is pressure times volume is equal to the number of moles times R, which is the gas constant, times the temperature. The key thing to watch out for here is the units. Pressure is in pascals, volume is in meters cubed, and temperature is in Kelvin. Now, pressure and temperature aren't too unusual for chemists, but volume is quite rare for us to use meters cubed, and therefore we need to watch out for that. If we substitute for pressure and temperature, standard conditions, room temperature and pressure, we can simplify that equation. So the moles of any gas at room temperature and pressure is equal to its volume divided by 24,000. And that's in centimeters cubed. Therefore, the moles of a gas is proportional to its volume if temperature and pressure remain the same. And finally, we can look at solutions. Now let's say I would like a cup of tea, and I say I'd like a sugary cup of tea. Now that's all well and good, but how much sugar should you be putting in a cup of tea, and in what volume? I could have a very large mug with 20 teaspoons of sugar, or a small mug with only 1 teaspoon of sugar. You need to know both those things. Now obviously we don't talk about mass as chemists, we always talk about moles. So we would talk about the number of moles of sugar I would like in a certain volume of tea. Now we've standardized that a little bit further in terms of its volume. And so the concentration of a substance is equal to its number of moles divided by the volume it's in decimeters cubed. And again, decimeters cubed can catch people out. 1 decimeter cubed is equal to 1,000 centimeters cubed. And we're doing a lot more of those conversions when we do our examples. Now I think it's time you could hit some problems.